It was really a wow moment. There was liquid water elsewhere in the solar system. We had been right. You have all of the ingredients that you need, that we know of, to develop life as we know it.
We have cleared the tower, and the Cassini spacecraft is on its way to Saturn.
So these sort of hard cases, these James Bond-looking cases, are used to transport the flight hardware. This is one of the magnetometer sensors that I worked on, and it will have been integrated onto the boom that came out from the side of the spacecraft.
And here's part of the magnetometer instrument, and here's the other half of the magnetometer instrument. This is a quarter-size model, so this is a quarter-size me. I'd like to be this weight, not this height.
She was one of the best things about the Cassini mission, because I spoke to her on the phone every couple of days for years and years and years. So a gas giant like Saturn is incredibly mysterious.
Saturn just captivates people because it looks so supernatural. It engenders the immediate feeling that it can't possibly be real.
It has no solid surface, and it has rings around it, and we don't necessarily know where those rings came from or how old they are.
These, as you can see, are spiky shadows that are created by these features here that are sticking up 2.5 miles.
Having the perspective of Cassini to be able to see that was one of the most extraordinary things, I think, about the images that came back.
It was just extraordinary. It was out of science fiction.
Some of the most amazing discoveries that Cassini made were about Saturn's moons. The first flyby of Enceladus was not terribly close, but something funny was happening in the magnetometer data.
Okay, so put it into slideshow.
My boss came to the team and said,
You can see there's a little pimple in the data, just over there.
This looks intriguing. This is not what we expect. We expect on a rocky moon for the magnetic field to drape over it, a bit like a nice peaceful curtain draping over a window that's not moving. And instead it looks like there's some sort of breeze gently fluttering that curtain.
And what we were able to do is calculate what ions were generating those waves, and it was water group ions.
So Michelle decided, after discussions with all of us, that she would go to the Jet Propulsion Lab and she would propose moving the next flyby of Enceladus, which wasn't for some time to come, to much sooner. And this was a huge risk for her.
We knew for us to be able to have a chance of really seeing what was going on at Enceladus, we needed to get closer.
The principal investigator of the magnetometer, God bless her, she went into action and convinced the project to take the spacecraft close to the South Pole so we could all get a better look.
And I must confess, I didn't sleep for 2 or 3 nights before that close flyby, because if we hadn't seen anything, no one would ever have believed anything I said again. So, but what we found was spectacular.
This image made me nearly fall off my chair, because here we see dozens of jets, big and small, coming off the South Polar region.
It was fantastic. It was really a wow sort of a moment. There was liquid water elsewhere in the solar system other than the Earth. Enceladus, tiny rocky moon of Saturn, is geologically active. A stable liquid environment, organic material, and contact with rock, you have all of the ingredients that you need, that we know of, to develop life as we know it.
I love this picture, and it's about as much meaning as you can get out of the Cassini mission, because we know that moon has an ocean in it that could harbor life.
One of the mysteries of Saturn originally was the source of the rings, and it turns out that Enceladus's geysers feed the very faint but very wide E-ring. It shouldn't be surprising that we found such interesting geological activity on a planet with 82 moons. Ironically, all these wonderful discoveries that we made meant you run out of fuel. It was on 1%, it had an empty tank, so we had to crash it into the planet and let it go.
This is the start of the end of the mission. We're running out of fuel, and we're going to make sure we go out with as much great science as we can.
We want to see how much of the atmosphere we can see before we lose the signal, before it can't fight the atmosphere anymore and it goes off point.
These last grand finale orbits where Cassini dove between the rings and the planet, they were never foreseen in the original mission planning. Actually getting to do that was really remarkable. Take these kind of dangerous dives between the rings and the planet to see what that space was like, actually with the spacecraft physically being there, was really remarkable.
In some ways, I just want it to be over now. You know, you're sort of waiting for it to end, and it's really weird.
Quite a lot of us were gathered round, tensely waiting for the data to come back. We were relying on the commands that we had written and we had sent to the spacecraft to have worked properly, and for the spacecraft to continue to be able to talk to us right up to the very last minute.
I can confirm science playback is locked.
And then it'll go away. We'll lose the signal, and that'll be end of mission.
Cross for 0 time.
So that would be the end of the spacecraft. Project manager off the net.
It doesn't feel a long way away, actually, because every time I watch it, I am immediately there again. So that I guess says something about the impact that the end of mission had.
That was a great spacecraft. It did exactly what we asked it to do, all the way to the end.
When you have checked on a spacecraft every day for more than a decade, and then suddenly it's not there, it really is a wrench. It's a blow, and you feel sadness and a certain amount of grief.
Godspeed, think it and release it.
Ever wonder what would actually happen if an alien civilization made contact? If they haven't already? Would the public be made aware, or would it be kept secret? How would we decode what they're saying? And how on earth will we reply? Well, believe it or not, there is an entire field of science that is dedicated to this.
By sending intentional messages, we'll let the civilizations know that we want to make contact.
There actually is a protocol that tells us what to do in case we pick up a signal that looks promising.
It's time to explore the unexplored. Seth Shostak is a senior astronomer at SETI, the rather cunningly named Search for Extraterrestrial Intelligence Institute. For decades, the Institute has been leading the way in actively searching for extraterrestrial signals, in the hopes of making the first contact with ET.
Most people, when they think of looking for intelligent life, they have some scenario kind of like in Star Trek, right? You get to a fancy rocket and you just, rocket off to some other world and look for it. We simply can't do that. But what you can do is maybe find the aliens at home by eavesdropping on their radio waves, or maybe they have flashing lasers.
If alien civilizations are anything like us, then they'll emit plenty of signals all the time. Radio, television, microwaves. All we need to do is just eavesdrop on one of these signals, and then boom, we've got contact. To make this possible, SETI uses 42 radio telescopes called the Allen Telescope Array. They direct these telescopes towards clusters of stars that we know have exoplanets, in the hopes that one of those exoplanets is broadcasting signals.
Now, we're looking for signals that are what are called electromagnetic signals, which is to say, flashing lights or radio waves. I mean, radio is just another form of light, if you will. So that's what we're doing. And why do we do that? Well, we know that it would work. We know that signals like those could go, from one star system to another and not become so weak that you could never detect them. I mean, it's always possible that they've developed some new physics that allows them to communicate in a way quite different from what we're envisioning. But, you can't do an experiment based on science you don't yet know. So we go with what we do know.
They haven't found anything definitive yet, but what happens when we do?
A lot of people do think that there's some sort of official procedure if you find a signal. I mean, wouldn't the Pentagon get involved and so forth? Well, they've never shown much interest in getting involved in it. And asking for a procedure is like asking Chris Columbus, hey, Chris, look, you're going to get in these 3 ships and head west on the Atlantic. What if you discover a new continent? Have you got a protocol for that? Well, he didn't, and it wouldn't have helped anyhow.
Are you as surprised as me to hear that there is no official protocol for when we receive alien signals?
Now, people who are involved with SETI tend to think ahead. There actually is a protocol that tells us what to do in case we pick up a signal that looks promising. It's very trivial. It just says, check out this signal, tell everybody, and don't start broadcasting back until you have the consent, if you will, of the rest of the world's population. So you don't have one society trying to monopolize communication with the aliens. What would happen after that is you would get everybody in the world who can study this thing because they got a big antenna or whatever. Then they would build new equipment that might be able to get the message. In other words, the bits that presumably are attached to that transmission. And once you have those, now you have, the equivalent of the hieroglyphics, and now you try and figure out what they might mean.
Bear in mind, these might not be intentional messages. We could be picking up their equivalent radio and TV transmissions that have just stumbled into our radio telescope. But for now, let's assume that they are sending a direct message. What happens next?
What if we decide to talk back? How will we encode that? Will we send them stuff in colloquial American English, a language they always seem to understand in the movies, or what else? Probably it's better just to send lots and lots of information. I would just send them the internet myself.
Really? It's mostly video games, TikTok dances, and ASMR.
Replying to any signal that we might pick up it's very controversial. You wouldn't think so, but it is. What are you going to say? And there's some people say you shouldn't reply at all. So, the matter of replying is controversial because of this potential for some sort of danger. On the other hand, I'm sure that if we were to pick up a signal next week or next month or next year, there are going to be plenty of people who have the ability to construct a transmitter in a backyard dish who are going to be sending their own messages to the aliens.
That's more terrifying than sending the entire internet. But what's odd is if aliens exist and there isn't some mass government conspiracy, then why haven't we heard anything? Well, as SETI continues their search for extraterrestrial intelligence, there's another organisation that thinks that we shouldn't be waiting to hear from them, we should be actively sending signals to potential alien habitats. What would you call an organisation that messages extraterrestrial intelligence?
My name's Doug Vakoch. I'm president of METI International. For over 60 years, SETI scientists have been searching for signals from other civilizations. So far, we haven't found anything. But what happens if every civilization is doing exactly the same as us? It would be a very quiet universe. That's why we should be sending messages of our own to try to elicit first contact. I'm at a scientific facility far north of the Arctic Circle called IceCat, an organization that sends radar signals into the sky to understand the composition of our upper atmosphere. But the interesting part, the new angle, is that we can also use it to send signals to nearby stars. One of our prime targets is the nearest star to Earth, Proxima Centauri, which is orbited by a planet in the habitable zone. We're sending signals that communicate some core ideas of science like chemistry, the periodic table of elements, something that we and the aliens have in common. By sending intentional messages, we'll let the civilizations know that we want to make contact. And in some cases, that may just be what's required to get a response.
Whether you think we should just wait and listen or actively send messages out into the expanse of space, the search is well and truly on. We haven't yet found evidence of life outside the Earth, let alone intelligent life, but scientists do believe that there is life out there. And remember, these signals can take a really long time to transmit.
In the best case scenario, we could send a message and get a reply in just 8 years. That's how long it would take to communicate with the nearest star to Earth. More realistically, it could take centuries, even millennia to communicate. So this is an inherently multi-generational project.
So there may well be another planet 1,000 light years away whose messages are hurtling towards us. And it could be any day now that we finally hear from them. Or maybe they're just watching, listening, biding their time. Or if they're anything like us at all, they've been meaning to message us back. And they will. Just after one more scroll.
The fate of the planets is intricately tied with that of the star that they orbit. So for our own solar system, the sun dictates our fate.
As our sun has changed, so has the potential for life on our neighboring planets. Their history shows that habitability is a delicate balance. That doesn't always last. There is only one planet that has retained its water and habitability, and that's Earth.
What's remarkable about Earth is the stability of those conditions, that Earth has been able to maintain oceanic conditions at its surface throughout its entire history, through billions of years, and that's what's facilitated the very rich biological evolution of Earth.
Earth is a very special place. It's the only place in the universe where we know definitively that there is life.
For that to happen, you need not just liquid water appearing on a planet, but liquid water staying on a planet, and that's the magic of Earth.
Thanks to the size and geology of our planet, the atmosphere has remained stable enough for billions of years, protecting the precious water that has enabled complex life to evolve. Life has woven itself into the fabric of the planet. And has shaped the continents and the oceans. So that now, life itself maintains the very atmosphere that protects our fragile ecosystems. But as the sun continues to grow hotter, temperatures on Earth rise. Upsetting weather patterns, raising great storms across the planet, and devastating droughts. As plants around the world die out, oxygen levels plummet. Around 1 billion years from now, the age of complex life on Earth will finally draw to a close.
Earth will ultimately be like Venus and Mars, just mostly CO2. There'll be nothing else really in the atmosphere. And it will remain in that state as a sort of hot oven planet until ultimately the sun, when it uses up its hydrogen and goes into a different phase, will become what we call a red giant.
You know, as we've seen in other stars throughout our galaxy, throughout the universe, our sun will continue to get hotter and hotter over time.
And at that point, it will expand greatly to the point where it will nearly engulf the Earth entirely. And at that point, the planets will lose their atmospheres and they'll be just sort of swept away.
As it exhausts its hydrogen fuel, the sun's outer edge inflates. As our star enters its red giant phase, expanding millions of kilometers out into space. Mercury is the first to be engulfed. Then Venus's fate is sealed. Some models predict that Earth may barely escape the fiery fate of its neighbors, hanging on beyond the edge of the dying star with Mars. But the long era of the 4 terrestrial planets will be over. The lives lived on one of them, nothing more than a distant memory.
Right now, the 2 Voyager spacecrafts are hurtling through interstellar space at 35,000 miles an hour. The space is so far away that it took 35 years to get there. And now we need new science to understand it.
I couldn't believe how nature was fooling us.
It made us rethink everything we knew about the shape of our solar system.
I think I discovered that the tail has a croissant shape.
And even where the edge of our solar system actually is.
There was a lot of confusion. Actually, the confusion lasted almost a year.
Even just to understand what Voyager is trying to say requires a very special set of skills.
It's really like a Swiss watchmaker. It needs to be a trained eye to tell me, can I trust this data or not?
What's even more extraordinary is how Voyager, the old spacecraft from 1977 with 64 kilobytes of memory, was able to make this journey at all.
3, 2, 1. We have ignition and we have liftoff.
Both Voyager 1 and Voyager 2 were launched in 1977, and it had to be then, thanks to an extremely rare planetary alignment that happens once every 175 years.
Where we could fly past Jupiter, get a gravity kick and go to Saturn, get a gravity kick and get to Uranus, and another gravity kick and go past Neptune.
Within just 2 years, Voyager 1 had reached Jupiter. Voyager showed us a planet, which looked so serene through a telescope, was actually rocked by hundreds of raging hurricanes, a glowing aurora at the North Pole, and 3 thin rings. Voyager took 33,000 images of Jupiter and its major moons that captured the world.
And we'd get to see these pictures and go, whoa, look at that, what's this, what's going on? It was fantastic.
On a night like tonight, our eyes, our minds, our souls, our blood are moving out through the universe. We're part of history, and that means that we have to replace the old myths with new ones.
Just 1 year later, and Voyager 1 had already sped past Saturn, spying intricate details in the planet's rings. From Earth, scientists could only see 5 or 6 of Saturn's rings. Voyager showed us that there were more than 100.
And I can remember those first pictures as we flew away, looking back at that system and seeing the reflected sunlight in that structured ring system was just so beautiful.
Then the Voyagers parted ways. Voyager 1 headed straight for the edge of our solar system. Voyager 2 took a more scenic route, reaching Uranus in 1986, and eventually Neptune in 1989, showing us yet more outstanding views of the green and blue planets and spotted geysers on Neptune's large moon, Triton. And that was the main mission, the first human-made object to reach the distant worlds of our solar system. But the Voyagers weren't done yet. They were about to embark on the journey to search for the edge of our solar system. And before they left, there was one last thing to do.
Carl Sagan convinced NASA to turn the cameras towards Earth and take that very famous picture, the pale blue dot.
On that blue dot, that's where everyone you know and everyone you ever heard of and every human being who ever lived out their lives. It's a very small stage in a great cosmic arena.
These images were the last of 67,000 images taken by the two Voyager spacecrafts. Their cameras were then turned off to save power as they carried on their journey towards interstellar space, the boundary where our sun's solar wind ends and the rest of our universe begins. Problem was, nobody actually knew where it really was. Scientists thought that sooner or later, the charged particles that create solar wind were going to run out, and Voyager would enter a pristine environment of interstellar space.
We thought that would happen, maybe just beyond Neptune. But no, that didn't happen. Well, we said to NASA, give us a bit more money, another 5 years. Well, this kept happening year after year. NASA, please give us a little bit more money, a little bit longer, soon we'll be there.
As Voyagers 1 and 2 continued to move out into the outer reaches of the solar system, they remarkably continued to send very faint signals back to Earth.
And this is what makes it so interesting and so fragile. The whole instrumentation of Voyager was designed to visit the outer planets that have very strong magnetic fields. So now you're dealing with a signal that is almost at the noise of the instrument. And because Voyager was not designed for that, it's a miracle fit that all this team is able to go mine the data and pull out the signal and tell us what's going on.
Just 5 instruments were still operating on the spacecraft. And in 2012, more than 35 years since Voyager 1 left Earth, scientists started to see the first signs that they were crossing into interstellar space, through the boundary known as the heliopause.
Think about the heliopause as your walls of your house. This is what separates the environment that is dominated by the solar wind from environment that is dominated from other winds from other stars outside of our bubble, the heliosphere.
The expectation was that there would be a sudden shock, a burst of activity that would make it obvious we had finally reached this sharp boundary. But the reality was much stranger. All of the detectors on Voyager were seeing particles suddenly appear, and then disappear, then appear and then disappear, and nobody had a clue why. These strange particles seemed to be coming from elsewhere in the galaxy.
Did we cross or not? The data was so confusing.
On one hand, Voyager was still being affected by the sun's magnetic field, but the particles were suggesting we had crossed.
It turns out what really tipped the scale in the team was the radio data.
The data was stored on the spacecraft using a tape recorder. So ancient technology, it's extraordinary. But it worked. And the data were gathered and sent back bit by bit.
And 6 months later, we turned to the radio station of Voyager, and guess what we heard?
These plasma waves, converted into sound that we can hear, were the final proof that we had crossed the boundary into interstellar space.
The first human-made object to venture into interstellar space.
Even more extraordinary than crossing the boundary into interstellar space was what the data said about the shape of the solar system.
I was tasked to create a computer model with all the physics that we know to kind of predict this shape of the heliosphere.
It turned out that the solar system's heliosphere is not round like you'd think. It has a tail from whizzing around the galaxy. And more than that,
I was finding that it has a croissant shape, 2 horns with a void in the middle. It was just a shock to realize that something such basic as the shape of our home is completely different.
And all of this was discovered by a small, extremely low-tech probe more than 10 billion miles away. And they're still going. In 2018, NASA's Voyager 2 spacecraft crossed the boundary. Finally, both Voyager spacecrafts, with their 1970s technology, had reached where no human-made object had ever been before: interstellar space.
There's very little material, very empty. Space can be very, very empty.
The environment out there is colder and denser. And of course, it's dark. There's not a lot of light. You're far away from the sun.
Voyager has also discovered that our solar system's impact is much bigger than we thought before.
We would have liked to get to a region where the heliosphere doesn't influence anymore the interstellar medium, what we call a pristine interstellar medium. What we're measuring now is a medium highly disturbed by the sun.
The Voyagers are still sending us ever fainter signals, still teaching us new things about interstellar space, but they're running out of time.
We probably have 2, 3, maybe 4 more years of power to communicate with Voyager.
But there are still so many mysteries left to be solved.
What is the environment outside? What's happening at the nearby stars that are influencing our system and so on?
So one of the beauties of the Voyager mission, that it started as a planetary mission, gave us the first images of our planets, discover volcanoes in the solar system, and then it went to discover our heliosphere, our vast, regions of our solar system, and enter into the galaxy.
Long after their power has gone, the Voyagers will continue to rush away from us, monuments to human endeavour and exploration, heading out towards the stars.
Voyager will continue its little journey in the interstellar space, way past when we maybe as a species will cease to exist, when we might move to a different planet.
It'll keep going and going and going and going and going forever.
So this is sodium cyanide, highly toxic, but we use this material for our research for origin of life.
Cyanide is deadly. As little as 1/10 of a gram can be fatal. John's colleague, Zhenfeng Xu, has been working with it for over a decade.
Just keep gloves on. Don't eat it. That's for sure.
Mixing the cyanide isn't enough. It then has to be exposed to the conditions of early Earth.
I'm going to put this in the solar simulator. This machine just simulates the early Earth conditions.
Levels of UV light were much higher back then.
UV light is the energy to drive the reaction. And it's free energy from the sun. And we're going to use it.
Inside the machine, the cyanide combines and recombines, creating the building blocks of life.
After a few hours, we can detect amino acid, nucleoside precursor, lipid precursor. They're all very important biomolecules in life.
Cyanide may be the raw material needed to kickstart life. So finding an abundant supply is vital for John and Zhenfeng's theory. And one type of location is more promising than any other. Impact craters. As a meteorite strikes, its energy superheats the atmosphere, generating huge amounts of cyanide. And it also melts the planet's crust, creating hydrothermal systems.
The meteor impact is really important for life to start.
John and Zhenfeng's idea is that rainwater flowed down the crater walls, absorbing cyanide, and then was heated in hydrothermal pools at the bottom.
And reaction taking place then. So simple.
To prove their theory, John and Jianfeng need evidence. Chemical traces from one of these craters.
On Earth, it's simply not possible to find evidence of these environments because all of the impact craters of that period have been erased by plate tectonics.
Scientists still don't understand how life began on Earth. But they do have 3 theories about how and where it might have happened. Hydrothermal vents with chemical energy for early life. Volcanic pools could have assembled cells. And impact craters could have provided the raw material for life. But here on Earth, essential clues to solve the mystery have long been erased. To find them, scientists need to return to Mars.
Poor Uranus. It's got rather boring clouds, truth be told. So there wasn't a lot to see with the cameras.
Passing close to the planet, Voyager's sensors reveal why Uranus is so featureless. Temperatures here are the coldest of any world in the solar system. There's simply not enough heat to drive the storms seen on Jupiter and Saturn. Uranus is an entirely new class of planet. An ice giant. And more surprises were to come. Uranus has rings.
We knew long ago from telescopic observations the rings were there at Uranus. We didn't know their configuration or their shape.
Voyager begins to explore the ring system and spots something curious in the shadows. Two moons, Cordelia on the inner edge of the brightest ring, and Ophelia on the outer edge, help to organize the system.
Particles within the rings can be moved inwards or outwards as these tiny objects called shepherd moons, whose gravitational force can shape and sculpt the rings themselves.
But it's the orientation of the orbits of these moons and the rings themselves that singles out Uranus as the strangest of worlds.
Uranus looks bizarre. The rings, rather than looking like that when you look through a telescope, they're actually orbiting up and over the top of the planet. The whole thing is tipped like a spinning top.
This bizarre orientation hints at an unusual past. Since the beginning, everything in the solar system has been circling in the same direction. It begins with a vast cloud of material that orbits the young sun. Over time, the material draws together, forming each of the planets. Today, They all orbit the Sun and spin on their axes in the same counterclockwise direction as that primordial cloud. Except for Venus and Uranus, which spin in the opposite direction. But Uranus is even stranger, because the entire planet is on its side.
This was a really strange system. So why is Uranus so tipped on its side?
If a roughly Earth-sized object smashed into Uranus late in its formation history, then that would have had the proper amount of momentum to basically knock it on its side.
And the collision may also help to explain another of Uranus's mysteries: why the planet is so cold.
That impact presumably relinquished all of that internal energy that the planet had when it first formed, and has left it as a relatively dead and sluggish world.
Much is learned during this brief encounter. But Voyager's strangest discoveries are yet to come. Most surprising is Mercury. The least explored of the rocky planets, because of the difficulty of getting into orbit around a planet so close to the Sun.
5, 4, 3, main engine start, 2, 1, and 0, and liftoff of Messenger on NASA's mission to Mercury. A planetary enigma in our inner solar system. Now going through the sound barrier.
Following a direct route to Mercury would be impractical. A spacecraft would arrive at such high velocity, it would need to haul a prohibitive amount of heavy fuel in order to slow down enough.
We just had spacecraft separation.
Grounded solids have jettisoned.
So Messenger controls its speed by stepping from one planet to the next, using their gravity to slow itself. Even so, Messenger still approaches Mercury, moving so fast that it is forced to fly past the planet 3 times, slowing on each pass. Until after nearly 7 years of flawless navigation, it arrives safely in orbit. At last able to begin its mission, mapping Mercury's surface.
That first image ever acquired from orbit around Mercury was amazing. When it finally came in, it looked perfect. It looked exactly like we expected it to be. For me, that was the real moment when I realized that we had successfully made it into orbit and everything was working.
This pioneering voyage has led to a completely new idea of how Mercury may have formed. Mercury is the most cratered planet in the solar system, with many puzzling features that hint at a violent past.
Mercury has a very unusual orbit. If you were on the surface of the planet, you would actually have to go around the sun twice to get one full Mercury solar day.
Also highly unusual is the planet's disproportionately large core.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock.
How do you end up with a planet that has so much metal inside and then almost none on its surface? That was a huge mystery.
And the major question is, why? Why is it like this when the rest of the planets aren't?
A clue to understanding these strange features was found in Mercury's chemistry.
So very soon after we got into orbit, we started to get chemical data back from the surface, and we immediately got some surprises.
The tiny probe detects volatile chemical elements in concentrations that no one had thought possible this close to the sun.
These are elements that go into rocks, but that evaporate at relatively low temperatures. And immediately told us that some of the older ideas of how Mercury formed could not be correct.
What Messenger discovered about Mercury could suggest a new twist in the story of the solar system. Just a few million years after its formation, the young Mercury is seething with the heat of its violent birth. Slowly, a crust forms, rich with volatile elements. If it had been close to the sun, these elements would have evaporated before the rock hardened. So what could explain why they're so abundant on Mercury today?
The orbits of the planets and their current locations have changed over the history of the solar system. So where things are today doesn't mean that's necessarily where they formed. They could have and probably did move from different locations to where they are now.
One possible thing is that Mercury didn't form where it is today. It formed much closer to the other planets, maybe even outside of Venus or Earth, or somewhere in between there.
If Mercury had formed near Earth and remained at a more comfortable distance from the sun, its destiny could have been very different. But it wasn't to be. So what turned it into the strange, sun-scorched world we see today?
We don't know the full story. What we have right now are theories, and as we have new observations, we are trying to change everything to fit those observations.
Messenger's evidence of the volatiles on Mercury's surface and the unusual size of its core suggest an interesting new theory. It's possible Mercury began life as much as 160 million kilometers further from the sun than it is today. In the region of space where the young Earth is also forming. A region with scores of planetary embryos all fighting for position. In the chaos, it's possible that something large pushes Mercury off orbit and in towards the sun. Mercury brushes against another planetary embryo. This glancing blow removing much of its crust and mantle. Now little more than a metallic planetary core. Mercury continues toward the Sun. Ending up in the peculiar elliptical orbit we see today.
Before we sent the Messenger mission to Mercury, I think we had a very simplistic idea of what it was going to be like. And Mercury turns out to be a more complex place with a more interesting and complex history than we had previously imagined.
But of course, all things have to come to an end, and once we were out of fuel, we could no longer burn our engines to keep from crashing into Mercury.
And sequencers, Chief Launch Detector on. Engines running, continue on.
After 4 years of observations, Messenger's fuel finally runs out. And the spacecraft adds yet another crater to this tiny world, where any prospects for life were scorched away when it was thrown too close to the Sun.
We're guaranteed to find an identical copy of our whole universe, as well as countless variations where things are similar to here, but still different.
Multiple universes now are a genuine possibility, which begs the question, is there another you in a parallel universe? Now, it probably doesn't surprise you that studying parallel universes was once considered completely bonkers in the scientific world, and it even alienated people who decided to pursue it.
When I was a grad student, I used to secretly print out my multiverse-related papers.
This job was the only job I was ever interviewed for. I was on the verge of having to drive a taxi cab.
Now theoretical physicists have realised that parallel universes are possible, mathematically at least. So why do we think other universes exist? Now, one of these reasons comes from the weird world of quantum physics.
The important thing to remember about quantum mechanics is that it's weird.
It really is weird. It's the study of subatomic particles, the building blocks for every single thing around us in the universe. And what it tells us is that these particles can be both particles and waves, but crucially, they can be both at the same time, which splits our reality, giving us multiple different universes.
The idea here is that when you make a measurement of a particle that's here and there at the same time, and you find the particle over here, then there's a you which finds the particle over here in this world, but at the same time, there's another world over there where another you has found the particle over there. And both of these worlds are equally real. So the quantum multiverse is not separated from us by distance. It's not someplace very, very far away. It's someplace that's effectively here in space, but the complexity of the quantum dynamics prevents these different branches from talking to each other. Whether you like it or not, the fact that we live in a multiverse is the dominant scientific paradigm. Suck it up.
Another theory is one of mathematical inevitability. If our universe is made from a finite amount of simple matter, then it follows that other universes are made in a very similar way.
Just as this house is made out of fundamental building blocks that we call Legos, everything in our world is made of fundamental building blocks we call elementary particles. And if you have some random process arranging elementary building blocks in a finite volume, there are of course very, very many different ways in which it could do this. And that means that if this process repeats in an infinite number of other volumes of the same size, then we're guaranteed that eventually it's going to create every possible arrangement. we're guaranteed to find an identical copy of our whole universe, as well as countless variations where things are similar to here, but still different. Even a Max over there who's identical to me, not just in his physical appearance, but in that he actually feels that he is me.
Another theory called inflation describes how the universe expanded exponentially in the very first tiny fraction of a second after the Big Bang, but with some areas of space expanding faster than others, creating bubbles or pockets of space-time where other universes could have formed. If this idea turns out to be right, then it could mean that these pocket universes developed with their very own laws of physics. So there could be another you in those universes that's able to walk through walls or fly through space. So if our universe is not alone, the question remains, what would the other you be like? Well, according to quantum theory, there's a new version of you and a brand new universe made with every single decision you make.
So every time I flip a coin, say heads or tails, that is just some little quantum accident. The universe is splitting into two worlds every time it comes up heads or tails. So our experience of this splitting is like the experience of walking through a garden of paths that fork. When we come to a fork in the path, we take one or the other, heads or tails. But both forks exist at the same time. We only experience one of them. There are literally gajillions of universes out there, of which ours is only one.
Then there's the patchwork model, a near identical copy of our own universe, just made elsewhere. In this kind of parallel universe, there's another you that's very similar, just with subtle differences.
We're guaranteed to find countless variations where things are similar to here, but still different. The dinosaur-killing asteroid that was our lucky break missed Earth, so there are no humans, just dinosaurs in Winchester today. There's another one where I didn't make it as a physicist, but I'm actually enjoying life working as a bartender. Then there's a whole bunch which are very similar, where I just chose to dress a little bit differently.
These ideas all point towards multiple weird and wonderful universes existing out there. But with scientists not able to see the entirety of our own universe, how on earth can we prove that these other universes exist? Scientists think that they might be getting a little bit closer.
Truth goes through 3 stages. First it's ridiculed, then opposed strongly, and finally it becomes self-evident. Perhaps now we are reaching the stage of self-evident.
Scientist Laura Massini-Horton found something really weird. She found evidence for what appeared to be 2 universes crossing over.
The detection of the cold spot was one of the signatures that we predicted by tracing forward the quantum entanglement of our universe with all the other surviving universes. We predicted that there should be a large area in the sky of about 10 degrees, and indeed that's what was observed about 7 months after we made the prediction.
Recently, there's also been a big leap forward for inflation theory, which predicted that if this rapid expansion of the universe happened, it would send ripples out into the universe. We call these ripples gravitational waves. We'd never detected anything like this until 2015, when 2 experiments called LIGO and Virgo managed to detect gravitational waves coming from the merger of 2 black holes. With that detection made, it makes it more likely that we might be able to detect gravitational waves from inflation. But why should we really even care about figuring out if multiple universes exist? Well, it actually feeds into the age-old question of what is our universe expanding into. If other multiple universes exist, perhaps our universe expands as neighboring ones contract. And this could actually tell us more about our own universe, and especially how our own universe will end. Perhaps eventually we will expand until those other neighboring universes also then have a big bang and start expanding into us, which means that we then start contracting. And perhaps our universe will end not in a big bang, but in a big crunch. Rain made of diamonds and ruby gemstones, 2,500-degree clouds filled with hellish liquid lava, and 350-year-old giant megastorms. This is the most extreme weather in the universe. Saturn is the second largest planet in our solar system, and its rings make it instantly recognizable, and personally it's my favorite planet because it rains diamonds from its clouds. Scientists estimate that around about 10 million tons of diamonds are produced in Saturn's atmosphere every single year. Now the sizes of those diamonds could vary a little bit, but they're estimated to be about a centimeter across. That's the size of a 4-carat diamond. But why does this happen?
We know that on Saturn there's carbon soot. The carbon soot is created by lightning. Lightning actually zapping methane in the atmosphere. The carbon soot precipitates or falls through the atmosphere.
As the carbon soot falls from the clouds, this same crystallization process occurs, but instead of taking billions of years, it happens in a matter of moments. Now, in order for a planet to have weather, it needs an atmosphere, the layer of gas that surrounds a planet. So for example, Earth's atmosphere is made of nitrogen, oxygen, argon, and a little bit of water vapor as well. The planet Mercury and our moon, on the other hand, they don't have an atmosphere, hence why they look like grey, lifeless rocks. On Earth, a cloud forms where it's too cold for water to stay as a vapour in the air. Now that can happen with other materials too, just at different temperatures. So it's essentially possible to have a cloud made of anything. But what about planets that are so hot that things that exist as solids on Earth are actually liquids and gases in their atmospheres? I'm talking about things like rock and lava. Imagine it being so hot that lava evaporates into the air, forming clouds, and then you get lava raining from the sky. 55 Cancri E is an exoplanet that's about 40 light years away from us. It orbits really close to its star. Not only that, it's also tidally locked, which means that one side of the planet always faces its sun and it's always daytime there and it's boiling hot. The day side is permanently covered in an ocean of molten lava. It can be hard to picture what lava rain would actually look like, but volcanic eruptions here on Earth in places like Hawaii give us a hint of what it might look like.
Right here was the site of a massive eruption. All along this fissure, fountains of lava shot into the air nearly 100 meters high. The liquid lava droplets then cooled and solidified in the air before raining down onto the surface as these tiny pebbles. This is what we think the rain might be like on planets like 55 Cancri E.
Planet hunters and astronomers think they have found an exoplanet with the strangest rain in the universe. WASP-12b is an exoplanet 12,000 light years away. It's a gas giant like Jupiter, but it's twice as big and its atmosphere is 2,000 degrees hot. An atmosphere like that, we think the conditions would be just right to give us molten ruby rain.
And the way that it scatters light suggests that there are clouds high up in the atmosphere. At this part of the atmosphere, the temperature is around 2,000 degrees. So the most likely substance forming these clouds is an aluminium oxide called corundum, which forms the basis of rubies.
This crazy extraterrestrial weather doesn't stop at gemstone rain. There are planets out there that have the most gigantic storms that humankind has ever witnessed. We have Mars rover footage that shows us dust devils that are over a kilometre high. But impressively, the storms on Mars can reach up to 20 kilometers in altitude, and it's all down to Mars's atmosphere.
Its atmosphere is 1/100th the pressure of Earth's, and the effect of having that really low atmospheric pressure on Mars means that it can't trap any of its heat. So Mars is a cold, barren desert compared to Earth or to Venus.
The dust storms are so bad on Mars that every few years or so they engulf the planet for months at a time. That's going to have a major impact on any future human missions that we send to Mars. These storms on Mars, though, are minuscule in comparison to what's been observed elsewhere in the solar system. We've sent probes and satellites to all of the gas giants and found some mind-blowing weather activity. The Great Red Spot is a storm on Jupiter that is twice the size of the entire Earth. It was first spotted by Giovanni Cassini through a telescope in 1665, which means it's been raging non-stop for at least 350 years.
That makes it the longest living storm that we know of. The outer planets are big balls of gas, and that makes a huge difference in the weather because you don't have continents, you don't have mountains for the winds to rub against, and there's nothing to control the weather the way the continents partly control our weather.
Saturn is the planet with the largest and most powerful storm in the solar system, covering 4 billion square kilometers. And we know about it because we've seen satellite images of it growing.
On December 5th, 2010, the radio receiver on Cassini started picking up the radio signal of lightning. And on the same day, the camera saw a little storm up in the northern hemisphere of Saturn.
Within 6 months, the storm grew so large that it wrapped around the entire planet and its head caught up with its tail. The truth is, life on Earth is a huge anomaly in our solar system, our galaxy, and even maybe across the entire universe. The majority of other planets are a lot less inviting.
So the planets that we've found so far aren't particularly nice places to go. They're not somewhere you'll put on your vacation list anytime soon.
So while we might not describe weather here on Earth as mild all of the time, astronomically speaking, mild is the most appropriate word. What makes Earth so habitable is this perfect mix of conditions that we have that essentially make it like a Goldilocks planet for life. And that includes our proximity to our star, the sun. Any closer and it would be a hellish inferno, and any further away it would be a frozen wasteland. So it could just be a matter of time before we find a planet that's similar to Earth. But what we do know is that warm, cold, wet, dry, windy and mild, all of these conditions work in perfect unison to keep us alive here on Earth. Essentially, we got lucky, so think about that the next time you want to moan about the weather.